This is a code lock built around 5 CD4017 decimal counter ICs without any microcontroller. When you enter the correct code, these yellow status LEDs right here light up stage by stage, and at the end the green LED turns on, indicating that the code lock is now unlocked. The cool feature of this circuit is that all wrong code attempts are detected automatically, which makes this code lock 100% secure. And in this video, I will show you the electronic components you need, the detailed schematic, and how you can build this code lock yourself step by step. Hi, my name is Jens and I believe that everybody can learn electronics, and this channel here is all about beginner-friendly electronics tutorials and projects with and without microcontrollers. And if you want to follow along today's project, here's what you need. Two 830-pin breadboards, one 9-volt battery and a battery clip, 5 CD4017 decimal counter ICs, one CD4081 AND gate IC, and an NE555 timer. 8 push buttons, 14 LEDs, 14 470 ohm resistors, 8 4.7 kilo ohm resistors, and 14 1N4148 diodes, 7 100 nanofarad and 1 10 nanofarad ceramic capacitors, 5 1 microfarad, 1 22 microfarad, and 1 100 microfarad electrolytic capacitor. And last, you also need some single-stranded wire, and I recommend American wire gauge 24 or 0.6 millimeters. Now, before I forget, there is also a companion article on friendlywire.com, and in it you can find a detailed list of all the components that you need, where you can buy them, and at the very end there is also a detailed step-by-step list of instructions of how you can build this code lock yourself. So it's basically a written version of this video. So go check that out later if you want. Now, this project is based on the CD4017 decimal counter IC, which we covered in a previous tutorial right here. Now, if you want to jump straight ahead to building the code lock, then you can go to this timestamp right here. But if you want to learn how this code lock works, then stick around, because now we're going to talk about the schematic. As always, it helps to split the schematic into smaller pieces. In a nutshell, this circuit works like this. Using the keyboard up here, you enter the code A, B, B, C, D, E, which unlocks the code lock stage by stage, and at the end, LED 13 turns on. If you enter a wrong code, then the circuit resets via the reset circuit at the top right here, and the alarm LED turns on and off. And if you're building the circuit yourself, then you can use this LED to trigger an external alarm or to connect it to another counter to keep track of all the wrong code attempts. But now let's dive into the details. First, let's talk about the power supply, the keyboard, and the reset circuit. The power supply is a simple 9-volt battery with a 100 microfarad bulk capacitor in parallel. This funny looking symbol right here stands for the power supply of IC6, which is the AND gate IC, and C12 works as its bypass capacitor. All other integrated circuits are also connected to the power supply, each with their own 100 nanofarad bypass capacitors as well. The keyboard has 8 push buttons, and you can add as many buttons as you like. I also added an LED to each button that lights up whenever that button is pressed, but these LEDs are not necessary for the circuit to work, so if you don't like them, you can just forget about them. And last, the symbols A to H are labels that refer to the buttons, and we use them in the lower part of the schematic. Later on the breadboard, we will of course connect all labels of the same name together. And last, the reset circuit. Even a very short pulse on the reset trigger input will generate a stable signal at the reset signal output, around 70 milliseconds long. This makes sure that the reset signal is on long enough so that all 5 counters have enough time to reset reliably. And this is very important, because if even one counter doesn't reset reliably, then the entire circuit doesn't work. And if you want to learn more about the reset circuit, you can check out the CD4017 video that I mentioned earlier. The buttons A, B, C, D, and E form the code, and that's why they are connected to the 5 stages at the bottom, and we will talk more about those in just a second. The keys that are not part of the code are directly connected to the reset trigger input, because they should reset the code lock whenever they are pressed. But for each unused key, we need to insert an extra diode. This is because of the LEDs. If we press, for example, the button F, then LED 6 would light up as it should, but also LED 7 and LED 8. And this would immediately give away all keys that are not part of the code, which would be a security risk. So the diodes D1, D2, and D3 make sure that no current flows into the other LEDs. So to understand how the code log works, it's a good idea to imagine what exactly happens step by step when you enter the correct code A, B, B, C, D, E. So let's do that next. Immediately after you plug in the power, the reset circuit triggers once and resets all the counters. So to begin with, all counter outputs are set to 0, which means that all Q0 pins are high and all other outputs Q1 to Q9 for all counters are low. Because all Q0 pins are high, all clock inhibit pins are high too, except for the first one, meaning that all stages, except for the first one, are locked and disabled after power up. Let's have a look at the first counter. At the clock pin, R9 works as a pull-down resistor that holds the clock input at low level whenever the push button is not pressed. And the capacitor C1 is a debouncing capacitor that we need for mechanical switches to work reliably, and you can check out the CD4026 video for more on that. The clock inhibit input of IC1 is permanently held low so that any clock pulse is registered and the counter increases from 0 to 1. Now imagine we actually press the button A. The counter increases so that Q0 is now low and Q1 is high instead. LED 9 turns on and shows us that the first stage is ready. And yes, this makes the code log not very secure because you can immediately tell if you pressed the correct key. So in a real-world application, you should probably not use these LEDs. I put them in this project because it makes it look more interesting and it's easier to understand what's going on. Alright, back to the circuit. So stage 1 is done and Q1 is high. This means that now the clock inhibit pin of the second counter is low, which activates stage 2 so it can react to clock pulses. So let's press B, which is the next part of our code. Then the counter increases from 0 to 1 so that Q0 goes low and Q1 goes high. But we're not quite done yet with stage 2 because the two diodes, D9 and D10, together with R19, work as an OR gate and still disable stage 3. So we have to press B again, and then the counter increases a second time from 1 to 2. Now Q1 goes low and Q2 goes high. This turns on LED 10, stage 2 is complete, and finally stage 3 is activated and ready to go. And this is how you can make the code log require a certain key to be pressed multiple times. You just add more diodes. And of course you can do this at any stage of the code. But back to entering our code. Now when we press the button C, counter 3 increases from 0 to 1 and LED 11 turns on, and that activates stage 4. And then pressing D increases counter 4 from 0 to 1, which turns on LED 12 and activates stage 5. And finally, pressing the E button increases counter 5 from 0 to 1, which turns on LED 13. At this moment, the code log is unlocked, and pressing any key will reset it back to the standby mode. So you see, it's just the same idea, just repeated over and over again, and you can totally make this a 17-digit code log if you wanted to. But now that we understand this, let's imagine what happens if we enter the wrong code. Now, if you press a key that is not part of the code, well then it's easy, you just reset the code log immediately. But what if you enter the first part of the code correctly and then something goes wrong later? That is where the AND gates come in. Let's say we put in A, B, B, C correctly, but then we mess it up by not pressing D next, which we should, but instead we press E, which is wrong. The button E belongs to stage 5, but because counter 4 is still at 0, stage 5 is not active yet, which sets the first input of this AND gate here to high. But then pressing E sets its other input high as well. With both inputs of the AND gate high, its output goes high as well, and that resets the code log, because the output of the AND gate is connected to the reset trigger. So this is exactly what all these other AND gates here do as well. They catch any key that is part of the code but is pressed too early when its stage is not yet ready. Now there is one case we haven't talked about yet. Imagine you enter A, B, B, C correctly, but then you press C again. What happens? Because stage 3 is active, the counter increases and LED 11 turns off again. But then Q2 goes high, and because Q2 is connected to the reset trigger, that resets the entire circuit. So you see, all possible wrong code attempts are detected by our circuit, making it 100% secure. Now the last thing I want to mention are the diodes. We use 14 of them, and so far we only talked about 5 of them. all of the remaining diodes are protection diodes and are connected to the reset trigger rail. They protect the outputs of the counters and the AND gates from current flowing into them whenever the reset trigger rail is high. Okay, so that was the main idea of the code lock schematic, and I hope it makes sense. If it was confusing at some point, let me know in the comments and I'll do my best to get back to you and explain it better. And also don't forget that there is a companion article that's basically the written version of this video. And now we're finally ready to build the circuit. We will build this circuit on two 830-pin breadboards, and usually breadboards have two power rails on either side of them. And it is a bit of a wasted potential in our project here to use all 8 rails for power supply purposes only. This is why I thought it would be a good idea to also use some of these rails as the reset trigger rail and the reset signal rail. And last, if you're building the circuit yourself, be aware that there are two types of 830-pin breadboards out there. Those with separate power rails and those with connected ones. We will use the connected ones, but if you use the other type, then no worries. Just make sure to insert extra connections in the middle so that the rails are connected all the way through from top to bottom. Place the two 830-pin breadboards in front of you and connect them together. Make sure that for both of them, row 1 points to the left. And as always, we will have a look at the schematic at the same time. Let's start with the keyboard and insert the 8 push buttons in rows 3, 11, 19, 27, 35, 43, 51, and 59 and connect their upper left terminals to the positive power rail. Next, place their 8 LEDs above the right terminal in column G with their cathodes pointing to the right. Connect their cathodes to the negative power rail with the 470 ohm resistors R1 to R8. Now insert the 4.7 kilo ohm pull-down resistors R9 to R13 between the right lower terminals of the push buttons and the lower ground rail. Next, place the debouncing capacitors C1 to C5 between the upper right terminals of the push buttons and the upper ground rail. Make sure that the negative terminal of the capacitors, marked with a big minus sign, is connected to the negative power rail. The diodes D1, D2, and D3 are next. Connect the right terminal of the remaining 3 push buttons to the lower VDD rail. Make sure that the diodes cathodes, the black rings, are facing towards the bottom. And now connect the upper and lower ground rails together and insert the 100 microfarad bulk capacitor C6 in the power rail. And as always, make sure that you plug it in correctly with its negative terminal plugging into the blue ground rail and its positive terminal plugging into the red VDD rail. Now it's time to insert the integrated circuits. IC1 goes in row 1, IC2 in row 11, IC3 in row 21, then IC6 in row 31, IC4 in row 40, and IC5 in row 50. The pins are labeled like this, and make sure that all notches point to the left. Connect the ICs to VDD on their top right pins and to ground on their bottom left pins. Next, place the 100 nanofarad bypass capacitors between the power terminals of each integrated circuit. You can bend the leads like this, but make sure the long lead faces towards the bottom of the breadboard. This way the wiring will be a lot easier down the road. Also bend the leads carefully so that you don't accidentally short out any of the pins of the integrated circuits. Next, insert the 5 status LEDs LED9 to LED13 and their 470 ohm resistors R14 to R18. Make sure that all LED cathodes point to the left. Connect the clock inhibit input at pin 13 of IC1 to the ground rail, and then connect all reset inputs at pin 15 of IC1 to IC5 to the reset signal rail. And now it's time to wire up the push buttons that are part of our combination. Connect the lower right terminals of switch A to switch E to the clock inputs at pin 14 of IC1 to IC5. Next, insert the protection diodes D4 to D8 from IC1 to IC5 to the reset trigger rail. Connect output Q2 of IC1, Q3 of IC2, and Q2 of IC3, 4, and 5 to the reset trigger rail. Make sure that the diode's cathodes, the black rings, face down. Now we have to connect the counters to each other. First, connect output Q0 at pin 3 of IC1 to the clock inhibit input at pin 13 of IC2. Then insert the diodes D9 and D10 from output Q0 at pin 3 and output Q1 at pin 2 to row 10 with the diode's cathodes facing to the left. Insert R15 between row 10 and the ground rail. And last, connect row 10 to the clock inhibit input at pin 13 of IC3. Moving on to the next counter, connect output Q0 at pin 3 of IC3 to the clock inhibit input at pin 13 of IC4, and then connect output Q0 at pin 3 of IC4 to the clock inhibit input at pin 13 of IC5. Now it's time to wire up the AND gates. Connect pin 9 of IC6 to pin 13 of IC2 and pin 8 of IC6 to pin 14 of IC2. Next, connect pin 12 of IC6 to pin 13 of IC3 and pin 13 of IC6 to pin 14 of IC3. Still with me? If yes, then connect pin 1 of IC6 to pin 3 of IC3 and pin 2 of IC6 to pin 14 of IC4. And finally, connect pin 6 of IC6 to pin 3 of IC4 and pin 5 of IC6 to pin 14 of IC5. Yikes. Now it's time to connect the outputs of our 4 AND gates to the reset trigger rail with the 4 diodes D11 to D14. Insert the diodes from pins 10 and 11 of IC6 to the upper reset trigger rail and 2 diodes from pins 3 and 4 of IC6 into the lower reset trigger rail. The cathodes, the black rings, are always connected to the reset rails. And we're finally on the home stretch. Insert the NE555 timer IC7 in row 60 with its notch facing to the left, and the pins are labeled like this. Connect pin 8 to VDD, pin 1 to ground, and insert the 100 nanofarad bypass capacitor C13 in between. Also connect the 10 nanofarad stabilizing capacitor C14 between pin 5 and the ground rail. Make sure that its lead does not touch the diode's cathode. You can bend it out of the way just to be safe. Connect pins 2 and 7 and then pins 6 and 7. Insert R20 between pin 7 and VDD and R21 between pins 3 and 4. Next, the 22 microfarad timing capacitor C15 goes between pins 1 and 2 with its negative terminal, the one with the big minus sign, connected to pin 1. Then connect the NE555's reset input at pin 4 to the upper and lower reset trigger rails like this and this. And finally, connect the NE555's output at pin 3 to the reset signal rail like this. Now it's time for the alarm LED. Insert the 470 ohm resistor R22 between the reset signal rail and row 48 and insert LED 14 between rows 48 and 49 with its cathode facing to the right. Then cross over to the lower part of the breadboard and then further down into the ground rail. Now we have to make sure that all power rails are connected to each other like this. And finally, we can connect the 9-volt battery clip. The positive terminal goes into the VDD power rail and its negative terminal is connected to the ground rail. And we are done. When plugging in the battery clip, you can see that the red LED blinks quickly, which resets the code lock and puts it in a reliable starting point with all counters reset. Then you can enter the code step by step and the code lock is eventually unlocked. But if you mess it up somewhere and press a wrong button, the red LED turns on and resets the entire circuit. And last, I wanted to mention how many different combinations there are for a code lock like this. With a 6-digit code and 8 keys, this allows for a total of 8 to the 6th power combinations, which is 262,144. And if you add more stages or more keys, you can increase that number even higher. So yes, this code lock is pretty secure. But this code lock schematic is not perfect, and I also want to mention that. Our code is A, B, B, C, D, E, and you can easily change the circuit to have codes like this, 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 and so on. The only codes you cannot generate with this circuit are codes like this or this, where some keys are repeated in separate but distinct groups. And I could not find a way around this without needing many more logic gates. So if you have an idea on how to do that or how else to improve this circuit, then please let us know in the comments. There is one question I can already imagine, which is, why didn't you just use a microcontroller? And that's true, you could use a microcontroller, and a good starting point if you want to do that yourself is my PIC introduction video right here. But in this video, I wanted to show you that you can build seemingly complicated circuits and schematics with just very basic components such as decimal counters and a couple of logic gates. So let me know if you have any questions. Thank you so much for watching, and I'll see you next time. And if you're still here, thank you. Because I don't upload every week, some viewers have asked me to set up an email list to send out notifications whenever there is a new article or video, and you can find the link to sign up in the description. I programmed this email list myself, and there is no third-party software involved, so rest assured you can always unsubscribe, and that permanently deletes your email from that list. Thanks for watching.